Yeah, good morning, all of you. We are discussing about multiple dosage regimen, right? So, multiple dosage regimen, just remember only 2 or 3 points. Okay. So, what it is saying here, we are taking the repetitive doses either in the form of IV bolus or IV injections and either extravascularly. Extravascular is nothing but oral administration or by your uh, two compartmental open model. These IV bolus or IV injection or extravascular or oral administration will comes under one compartmental open model. So we are taking a drug which is following one compartment open model. Through this routes of administration, we are taking repeatedly. So when we are taking repeated administration, your dosing intervals of the drug may be dependent upon the biological half-life of the drug. So, if your drug will have 4 hours of biological half-life, you have to take your drug first dose at suppose 6 hours. Then after 4 hours, it will be 12 hours. So, you can take the second dose of your drug at 12 hours. So here what we are doing, we are taking our drug repeatedly. It is dependent upon the biological half-life. So this is the first dose of your drug can be taken at 6 hours and the second dose of your drug can be taken at 12 hours. So here we are taking consideration into the dosing intervals. So here the difference is 6 hours. That is nothing but dosing interval. This can be denoted you with tau. So if you want to take another second dose or third dose or up to nth dose, make sure that there is a complete removal of your previous dose. Why? Because if it is not removed within that particular biological half-life of the drug, you may get some drug accumulation. Drug accumulation. So for the removing of this drug accumulation, you can take with respect to the biological half-life depending upon the second dose or third dose or nth dose. So this is the major concept of your multiple dosage regimen. In the last class, I discussed with only these IV injections. Either it may be a bolus dose or it may be an infusion dose. So I discussed only regarding IV. So this is all we know. What is the beginning dose and what is the ending dose? How we can calculate this beginning and ending. This slide is continuation from the last class. Okay. So you can consider here this C10 beginning. Beginning means here we are calculating the starting dose. So for that reason here we are taking the initial dose of the drug. So dose is nothing but in the sense of concentrations we are calculating. That's why first concentration dose at initial time. So see here. So every time here you are going to add this capital R. R is nothing but the rate of infusion or the rate of bolus. Okay, either the rate of infusion, either the bolus, either the rate of bolus or infusion. Why? Because here we are taking consideration into IV injection. IV injection. Either it may be a bolus dose or infusion dose. That's why capital R is represented you just rate of infusion or rate of bolus. So capital R means what? E to the power of minus K into T. Here we are calculating our plasma drug concentration with respect to the time and to that of K. Capital A is always capital KE, elimination rate constant. So capital R is nothing but e to the power of minus kt. So here wherever e to the power of minus kt is there, you can replace it with R. In some cases, you are going to see instead of t, tau. So here we are considering dosing intervals, not a particular time interval. So that's why the dosing intervals can be represented with this tau. So e to the power of minus k tau can be replaced with capital R. Then you may get equation 1 and equation 2. This is the beginning dose and this is the ending dose. The plasma concentration at the beginning and end of the nth dosing interval are given by these two following series. So here beginning means we are adding R plus 1, R plus 2, R plus 3 like that. If it is a second dose, you have R square. If it is a third dose, you have a R cube. So here every time we are adding the R values. So starting we can add all these R values, right? See here. R1, this is only R. Next one is R square. Next one is C10 R3. So like that the equation will be. And the last dose is Rn minus 1. And if you subtract this nth dose R value, then you will get the last dose of this equation, beginning dose. And if you want to calculate the end dose, you can use this equation for calculating this. Last one is R to the power of n. Here no subtraction, directly R to the power of n. How many doses? Number of doses is representing you the small n. Okay. So R is always smaller than 1. Then Rn becomes smaller as n increases. If it is increasing, your R is small. So, where n is equals to infinity, n is equals to infinity. Here, in case of beginning dose, we have r to the power of n minus 1. In case of ending dose, r to the power of n. We have these equations at the last of the equation. This is the beginning dose and this is the ending dose. Equation 1 and equation 2. So, when n is equals to infinity, if your n will be infinity. So your equation 1 and 2 become, see these equations. 1 is this and 2 is this equation. This is 1 and this is 2. C max, C max and C minimum. Concentration maximum, concentration minimum. Concentration in the sense plasma drug concentration. If it is a C maximum concentration, the equation is C10. Initial concentration at first dose of the drug divides with 1 minus capital R, and C minimum is equals to C maximum into R into C1R minus 1 divided by 1 minus R. So these two equations you can remember like this. This is C maximum and this is C minimum. At average steady state plateau, drug concentration will be C average is equals to AUC T1 AUC, see just write down like this, T1, and here T2 divided by tau. So here we are considering dosing intervals which are divides with your T2 and here T1. What is the time at T1, first dose time, and then AUC. So this will gives you the C average, plasma drug concentration average at the steady state plateau. The C average is not the arithmetic mean of maximum or minimum, because plasma drug concentration declines exponentially. After some time, this is the minimum and this is the maximum, right? Minimum effective and maximum safe. So your drug can travel in between this. So it will be declines after some time. It is not the arithmetic mean of this maximum or minimum. It will be declining. Your plasma drug concentration will be declining exponentially. So that's why it is not the mean of this C max or C minimum. Here we are calculating only the average drug concentration with respect to the AUC. When we take consideration into area under the curve, it is very easy to calculate the plasma drug concentration average. So how you can calculate it? With the help of volume of distribution and initial amount of the drug and elimination rate constant. See here, AUC T1, T2 divides with tau, T2 divides with tau. Okay, just write down like this, which is equals to X naught divided by VD into K. Okay, X naught divided by VD into K. So then your C average is equals to X naught VD KT. K tau, not T. This is a tau. Okay. So this is about your maximum, minimum and average. So when you calculate this maximum, minimum and average, the drug will attains the steady state plateau. The steady state plateau, we can calculate this minimum, maximum when your drug can be taken through multiple dosing through the IV. Then we can calculate by the use of these equations. So in terms of the amount of the drug in the body, previously what we calculated in terms of your concentration, we can calculate it, right? So now we are going to calculate it in terms of amount of the drug. Your amount of the drug will represents with capital X. So X max, amount of the drug at maximum, X naught by 1 by R, amount of the drug at minimum, X max into R is equals to X0 R by 1 minus R, and X average, X naught by tau. So these are in terms of amount of the drug and these are in terms of concentration of the drug. So these amount of the drug and concentration of the drug can be calculated at steady state when the drug will follows IV injection through one compartment open model, when it will be given through multiple dosage. That means repetitive administration. So this is about your IV injection of one compartment open model. So generally what we learned with this multiple dosing respect to the IV, on repeated drug administration, the plasma drug concentration will be added. What is going on here? The plasma drug concentration is added upon for each dosing interval. It will giving a steady state with the plasma concentration. It will be fluctuating between the minimum and maximum. Here you are taking first dose. After some time you are going to take second dose. Then the next one third dose. So what you are doing here, 1 plus 2 plus 3. Every time you are going to add your doses. You are going to add your concentrations. Nothing but your concentration of the drug. So see, on repeated drug administration, the plasma concentration will be added upon for each dosing interval. It will giving you a steady state with the plasma concentration. This steady state can be fluctuating between the minimum and maximum. See here how it will be fluctuating here. See, when you plot a graph between time versus plasma drug concentrations, we have a minimum and we have a maximum. This is of CSS and this is also of CSS. CSS is nothing but steady state. Steady state means SS. Here we are talking about concentration. So the steady state plasma drug concentration maximum, the steady state plasma drug concentration minimum. Here our drug is fluctuating between these two concentrations. So when you take this multiple dosage regimen of IV injection, your drug will be fluctuating like this. So the sentence is explaining in terms of this graph. This is about your IV injection, multiple dosing. And the next one is, this is B. Next one is multiple dosing with respect to the oral route. When an oral multiple dosing regimen is followed, plasma concentration will increase, reach a maximum and it begin to decline, reach a maximum and it begin to decline. A second dose will be administered before all of the absorbed drug from the first dose can be eliminated. What is the meaning of this sentence? After your first dose gets eliminated, your second dose can be administered. So after reaching its maximum, it will begin to declining. The consequent plasma concentration resulting from the second dose will be higher than the first dose. So your plasma drug concentration available at the second dose will be higher than the first dose. This increase in the concentration with the dose will continue to occur until a steady state is to be reached. See, when you take this first dose, here the concentration will be the minimum. When you take the second dose, your plasma drug concentration will increases. Up to at what level it is going to be increased? Until unless it will reaches its steady state, it is go on increases. And then their steady state, at the steady state, your entry of the drug and your exit of the drug will be equal. Entry is nothing but absorption of the drug and exit is nothing but elimination of your drug will be equal. So this is what your multiple dosing with the oral route. See here. Here the drugs will follow the C minimum, C maximum principle. So with this, irrespective of MEC and MSC, it is traveling. Irrespective of minimum effective and maximum safe concentration, the drug producing its multiple dosage regimen when you can take this through the oral administration. Then what are the assumptions these can be situated? What are the assumptions these can be followed? This repetitive extravascular dosing through one compartment open model having these following assumptions. Drug absorption. See ma'am, here we are taking the drug through oral route. So definitely there is a need to calculate absorption and elimination, right? So that's why here you will get two types of constants. One is Ka and other one is Ke. Ka is nothing but your absorption rate constant. Ke is nothing but elimination rate constant. Here we are taking consideration into oral dosing. Oral means it is going to be absorbed and it will get eliminated out. So we need to calculate two rate constant. Drug absorption and elimination. These two processes can follow the first order kinetics. That means these can be traveled on the basis of your plasma drug concentration, concentration dependent parameters. The PK parameters, the pharmacokinetic parameters such as Ka, K, K is nothing but your Ke. Just remember it. Wherever capital K is available in your textbooks, that is of nothing but Ke. Elimination rate constant. And VD, volume of drug distribution, and the fraction of drug absorbed. That is nothing but small f, fraction of drug absorbed, remain constant during the multiple dosing. So these four parameters can be constant during these multiple doses. So the following equation describes you the plasma drug concentration versus time profile. When you plot the graph between C versus T, you following a single dose of extravascular drug. So this equation is applicable for single dose, but you are taking your drug in multiple doses. So repeatedly, if you consider the single dose, then you can calculate all these parameters, but these all parameters can be remains constant during this multiple dosing. So how you can calculate the plasma drug concentration? See here. This is extravascular administration. Short form I have written here EVA, extravascular administration. So you just remember this entire equation. See here, capital C plasma drug concentration is equals Ka F of X0. Ka is absorption rate constant. F is fraction of the drug absorbed. X naught initial amount of the drug you have taken. Then Vd volume of drug distribution divides multiplies with Ka minus Ke. Elimination absorption rate constant subtracted with elimination rate constant, which multiplies with e to the power of minus ket minus e to the power of minus kat. So these are two exponential forms of absorption phenomena and elimination phenomena. E to the power of minus ket is exponential form of elimination rate constant. Ka is absorption rate constant exponential form. So you can remember this equation very simple. How you can remember it? We are calculating extravascular dose. So what are the parameters? We can calculate absorption rate constant, elimination rate constant, volume of drug distribution and fraction of drug absorbed. So Ka absorption, fraction and amount. Ka f of x naught divides with volume of distribution, it is multiplied with absorption rate constant, elimination rate constant. So here we are using two processes, then we will get two exponential forms for each. See, elimination exponential form, absorption exponential form. So this following equation will describes you the plasma drug concentration versus time profile, which is following a single dose of extravascular administration of your drug. So if n fixed doses, if you are fixing the doses, the number of doses will be fixed by yourself. That is nothing but small n. That is x naught is fixed with small n, are administered at fixed time intervals. Here we are taking fixed doses at fixed time intervals. Time intervals are nothing but tau, but fixed doses are indicated you as small n. The plasma concentration is given at nth dose because we are taking n fixed doses and we are calculating for nth dose plasma drug concentration, which can be given as CTN. You can written like this, CNT. N is nth dose we are calculating, T is time. This is plasma drug concentration. So your equation is same, Ka f of x naught divides with Vd into Ka minus Ke. But here you got some difference. See here. Here you are taking n number of fixed doses. 1 minus e to the power of minus n k tau. N k tau divides 1 minus e to the power of minus k tau. Here k I am talking you about k is nothing but ke, elimination. Okay. So in the previous equation we have directly e to the power of minus ket, but here we got 1 minus e to the power of minus n into ke tau. Here we are considering dosing intervals and we are taking fixed doses at fixed time intervals. These are fixed time intervals and this is the fixed doses. So that's why n ke tau divides with 1 minus e to the power of minus ke tau. Simple. Which multiplies with same e to the power of minus ket. This is whole about your elimination rate constant. And in the same manner, you can apply with your absorption rate constant. Instead of Ke, here Ka comes. See here. E to the power of n Ka tau. 1 minus e to the power of Ka tau into e to the power of minus Kat. Here you are going to write T and here you are going to write tau. Here we are taking dosing intervals into consideration and here we are taking a particular time of your dose. So this is what the equation is useful for calculating when you take the n number of fixed doses. CTN is the concentration of drug at time t after mth dose. So if your n, that is fixed doses will be larger, then your terms, those are e to the power of minus nkt and e to the power of minus nka tau. these two terms will becomes negligible. So where is these two terms here? See here, e to the power of minus nket and e to the power of minus nka tau. Sorry, it's not t, tau. So these two parameters will becomes negligible. Then your equation will becomes, see here, e to the power of minus kt divides with 1 minus e to the power of minus ket. So you can write this equation in the form of this equation. So here instead of c t n, we are writing c infinity n. If n is larger means here you are going to calculate your nth fixed doses at infinity time. So that's why you are taking here infinity, c infinity n, c infinity n. So here you are going to neglect these two terms. Okay, then your equation will becomes, just write down this equation by removing this e to the power of minus n ke tau and e to the power of minus n ka tau. So after removing this, you will get this equation. Then the above equation is used to calculate C maximum and C minimum on the plasma concentration. Plateau is nothing but steady state. Steady state is also called as plateau. By substituting the values for T, which corresponds to the peaks and valleys in the C versus T curve. So when you take consideration into these peaks and valleys at the steady state, your T will becomes TP. TP is nothing but P stands for peak time. T stands for time. So instead of writing e to the power of minus k tau, then you can write e to the power of minus k into Tp. So this is what the equation. The equation is same like previous equation. Only one thing you have to write, instead of writing T, here you are going to write Tp. We are considering peak time. We are considering peak time of plasma drug concentration at the plateau state. Plateau state is nothing but the steady state. Okay. So then our equation is like this. This is for C max, maximum drug concentration at the steady state. Ka f of x naught divides with Vd into Ka minus Ke. This is same. Okay. Then e to the power of minus e to the power of minus Ktp divides with 1 minus e to the power of minus k tau. Then 1 e to the power of Katp by 1 minus e to the power of Ka tau. So this is what the equation for C maximum. Then you can calculate for C average. So I already told you, in case of IV injections, so you are taking AUC into consideration. AUC T1 and T2, which will divides with dosing interval. So you can write this equation or you can write this equation. Instead of writing AUC T1 to T2, f of x naught divides with Vd into Ke into tau. Volume of distribution, elimination rate constant into dosing intervals. Why? Because this whole term represents you AUC, area under the curve. So this is what your extravascular administration of the drug, which follows one compartment open model. So this completes your multiple dosage extravascular administration by one compartmental open model. Okay.